एक तुम्हारा ही है. So anyway, we saw that everything is not plug and play. Things can go off the air sometimes. But anyway, we hope now we are on air, and I believe some more people have joined this session. So I was trying to tell you is that what we are going to do is take up some of the questions which were already raised on the forum, and in response to this live session. So we'll take issues one after the other. So I believe some of the learners have some problem in understanding the exhaustion and padding methods. So we'll just talk about it. So exhaust method is a method where there is some chemical, dye, whatever in the solution, and you put your fabrics in that solution and work on it and hope that the dye or the chemical actually finally reaches the fabric. So we have some terms. Let's say we're talking about dye. You want a 2% shade or a 1% shade on a dye of the dye, or this is what it means is that you will have something like 100 grams of fabric can have 1 gram of dye. But let's say we have 1 gram of fabric. Another term which people have to decide or learn is what is the ml ratio. Because if the liquor is more, it appears because the chemical or the dye for that matter is water soluble. Therefore, it would have tendency to remain in solution as well, because everything is an equilibrium reaction. So people would like to know what is the M to L ratio, material to liquor ratio. Let us say we assume that the material to liquor ratio in some case which has been given is 1:100. That means 1 gram of fabric is 100 ml of the solution. And let's say it's a dye, and let's say you want to do a 1% shade. So for 1% shade, 1 gram of fabric, actually how much dye would you require? Required 0.01 gram of dye. Is if it is on the fabric, then we will say it's a 1% shade. So suppose there is another term which also one should know, is the exhaustion. How much in an equilibrium situation the dye from the solution will actually be on the fabric. So if it is very high, the very high means, let's say maximum could be 100%, all the dye from solution actually goes to the fabric. So the whole equilibrium shifted to the fabric. So we are very happy about it. So if suppose we have a situation that 100% is our exhaustion, we have 1:100 material to liquor ratio, and we want only 1% shade. So theoretically is 0.01% dye gram would be required in 100 ml, and that becomes the percentage concentration. So I hope it should be clear. So in case the ml ratio is reduced from, let's say, 1:100 to 1:50, then obviously what you will require is the concentration will have to be doubled. If suppose it happens that the exhaustion is also 50% based on our experience, then again you will double this concentration in the liquor. So that finally on the fabric it is 0.01 gram, right? That's what it is. So let's see what is the padding process. The padding process, on the other hand, has one parameter which is called the wet expression. So you have a squeeze roll and you pad the fabric through a solution and then they squeeze it. If suppose you want a 1% dye, 1% chemical, and you have 100% expression, 100% expression means 1 gram of fabric gets 1 gram of solution. That's 100% weight add-on. Okay, and if you really want the concentration of the chemical also 1%, then what would you require is the solution should also be 1%. Only then you will get the same dye. So situation is very simple. Although ultimately you're going to get the same amount of chemical on the fabric, but the concentration of the chemical in the padding will be higher and the concentration of the chemical in the exhaust system will be quite low. I hope it makes some sense. Some people wanted to ask a question whether what is the difference between content and add-on. Okay, content and add-on. So I think we did try to answer this question in the forum, that a 2% content means that either it is moisture or it is dye or the chemical has got 2 gram of chemical and 98 gram of the substrate. Together they make 100 gram. That's the situation. We'll have about 2% content. A 2% add-on would mean, let us say you have 100 gram of fabric. At the end of the day, 2 grams have been added, so the final weight will be 102. That's it. It is just like moisture content and moisture regain, right? These questions you may have been doing in some other course. People wanted to know, some people wanted to know, what is the difference between covalent bond and van der Waals forces. So first, I'm sure most of you know, all the bonding processes actually are in some way some kind of a contract between different atoms, different molecules. Why do you want to come together? Why do you want to have a bond? Bonding means they want to come together. Why would anybody come together? There must be something to gain. In a normal situation, when the covalent bonds are formed, every bond has an electron pair, right? So if the pair is there, the situation is more energetically stable position. And in case it so happens that to make this kind of a linkage with two atoms, the complete sharing takes place. One electron is from one, the other electron is from the other. Whichever way you do, both of them together form a couplet or a pair. In such cases, the liking is very much, the bond is very strong, and the covalent bond therefore becomes. So it's electron sharing. If that happens, then there's a covalent bond. The other thing was, what is van der Waals forces? Is one of the weakest forces. Here it's like, for example, negative attracting positive and polar things actually coming together. That's kind of a bond which is there, because you take any molecule for that matter except some, the electronegativity of one atom is more than the other, and because whenever such situation comes, there will be a polarity. If there is a polarity and the other molecule also is polar, then the polar will have some kind of attraction and they will try to make some bond. So this is weak, but if it is in abundance, then the whole strength can be very strong. For example, the case of polyester, it just has van der Waals forces only, but you can't dissolve polyester in water, you can't just break it like this. If the number of chain, it can polymerize under the conditions of curing, linear compound. But as we make it more and more cyclic, then the rigidity also occurs, and under the condition it is not easy for them to combine with another such molecule, but they rather would have more possibilities of combining with any other hydroxyl group which is available otherwise. And so you would see more cross-linking, and self-polymerization of a cyclic compound is not easy under the conditions we're talking about. Then how do we remove formaldehyde? This was one query related to this. So formaldehyde detection is easy. You can see some odor. If you walk through a lab or through an industry, you will see some type of a smell that is just like a fishy odor, as they call it. And you will know something is coming. Why? It may be free formaldehyde, dissociated, you see, from a compound which is being used, that can get dissociated and the formaldehyde will be free. And if that happens, then you will have the smell. So formaldehyde from environment point of view have some issues, and therefore the methods which have been used can be very simple, like wash. You make a fabric, you finish the fabric and wash. It's just that people don't like to wash, because the final fabric, why should I wash? I would like to sell it. But if you wash it, then the free formaldehyde can be easily removed. That does not mean that the formaldehyde will never be released. Every time there is going to be any hydrolysis, which may be happening during every wash maybe, and therefore we say performance can go down over a period of time. 50 washing, 100 washings, you may see something has come out. So some are, even the covalent bonds are also in some sense, as we say, contract, and also an equilibrium kind of a system. They can also hydrolyze, they can also break. We know that any kind of a bond can be broken under circumstances. So if you have circumstances which facilitate hydrolysis, the hydrolysis will take place. So some of these things can come out. But if we see that they are coming out quite a lot, then the first thing that the industry can do is wash them off, or use some formaldehyde scavengers which can react with them, and then they would be bound to some extent, and after that you can remove them. And so the problems can be reduced. So the question is, why at all we would like to use, why would we like to use formaldehyde based agents at all? This is a good question. I mean, if you can avoid them, sure, don't use. You will have no formaldehyde problem. Like in the cross-linking, if you have glycol, glyxyl type of a situation, then there is no problem. You will not have a formaldehyde issue. But it so happens that the formaldehyde compounds are also very good. They react under very nice conditions. So what one has to worry is how much is going to be released to the environment. So in the world standard systems, they have not said that do not use formaldehyde based compounds at all. When such type of restrictions come for some compounds, some restrictions are there, certain types of amines are there where the complete restriction is there. So nobody would manufacture, nobody would synthesize, nobody would work with them, nobody would use them as any kind of an agent. But formaldehyde still has not come into that category where they have to be completely avoided. So what they have fixed is, depending upon the use, I think we discussed in one of the lectures, the amount of formaldehyde that can be released is limited. If you are within that limit, you are all right. If you exceed that limit, you'll have to do something about it. Use scavengers, use whatever you have to do, and normally we expect that once the initial precautions have been taken by the person who is the finisher, and all this thing has been done, then during the use, the amount which will come out will be more likely under the acceptable limits. We will not have much of a problem. There was some question based on whether the resiliency of a fabric would depend on the weave. And after all, what is the weave? You have a plain weave, you see the rigidity of a fabric itself changes, isn't it? If you have more number of picks and ends in a fabric, what do you think? The rigidity changes? Not. The drape of a fabric. If you understand the drape, right? You take a round plate, you put the fabric on top. Think of a canvas being placed on the top of that plate versus a chiffon fabric, right? So why is the difference? Difference obviously is, now you know that any time you want to bend. After all, the draping and softness have something to do with the bending. If anything you want to bend based on the thickness of the material, the outer layer and the inner layer have to traverse different distances. They have to move, otherwise nothing will move, nothing will bend. If there is no motion at all between the layers, between the fibers, between the molecules, if it is completely made rigid, nothing will bend. So when we talk about resiliency, what we are looking at is the resistance to deformation and recovery from the deformation. So there are two things that we are looking at. So if any of them is not in your favor, the overall resiliency will be poor. So if you have a tentage fabric, canvas fabric, tightly woven, difficult to bend, it offers more resistance. And if you are really strong enough and you actually bend it, you'll find there may be a crease there. It's not coming out very easily. Why? Because there may be some slip between the yarns, there may be some slip between the fibers, and if that happens, then there is no recovery force. You see, they recover only when there is a strain energy stored. So we will affect. You can understand the resiliency, and that is why what we said is whatever happens, if internally the fiber recovery has to be improved, then we said we'll put some cross-linking agents in the system, which probably would help you to do things better. There was another question which people had asked, whether you have a reactive dye which makes a covalent bond. So can we not improve, or can it not improve the crease recovery of the fabrics? What do you think? If you have a monochlorotriazine dye, which sometimes you know as Procyon H dyes, or a dichlorotriazine dye, sometimes known as a Procyon M type of dyes, what do you think? Can they make cross-link? Can they make cross-link? So for cross-linking, we said that there should be at least two distinct functional groups. A chain, and one end there is a functional group which can react, on the other end there is a functional group which can react. If this is facilitated, then only you can make a covalent cross-link. That will be called a cross-link. So of course we have dyes which are called bifunctional reactive dyes. You may have seen some of those structures. The bifunctional reactive dyes were not designed to do cross-linking. They were designed for better exhaustion. But at an opportune time, yes, they can make cross-links also. But whether it is going to be in your benefit, that has to be seen, because to get a certain minimum crease recovery requirement which have to be met, you may have to add good amount of dye, which is not your aim. Dyeing is based on your percentage shade that you require, the tones that you require, and not based on how much crease recovery improvement will bear. So although theoretically yes, they would do it. If you do solubility test after dyeing with bifunctional reactive dyes, you may find the fiber is now less soluble compared to if you had used a monofunctional reactive dye, right? So that's, hope this answers your queries. There was one question, I'm sure there was some confusion as such about the phase separation catalysts. See, phase separation catalyst means that one phase gets out of the solution, so you have the two types of agent or ions and are present in such kind of thing, like magnesium dihydrogen phosphate or aluminium dihydrogen phosphates. So you have dihydrogen phosphate, which also in a way ionizes to hydrogen phosphate ion also. So all of them remain in equilibrium position, but as the water dries up, like you have done the padding, after padding you are going through a drying process and then a curing process. So moisture keeps on going out. As the moisture keeps on going out, then what happens? The concentration of each one of them rises. If suppose one of the species has low solubility product, then what will happen? If the solubility product of one of them is lower, so it is going to precipitate. That's called the phase separation. So from everything which looked like a solution, now you have part of it solid, which obviously settles down and does not participate in any reaction process. And what is the reaction process we were trying to generate? Hydrogen ions, which can act as catalyst and carry on the reaction forward for us, right? So now, because one of them is not participating, the other one starts dissociating more and more. So more hydrogen ions can now come. And so, in that case, from almost behaving like a weak acid, they start behaving like a strong acid when the concentrations are high. So there was something called, it should be square. I think the video says that it is square of hydrogen ion concentration at the end of the reaction. So there was no square root there. So I'm not sure why the confusion was there. Just before that, we had written that the concentration becomes approximately half of that. So that half, I hope, is not getting confused by square, that there's no square root there. Okay? So this is how it is going to be. Then softeners. By now we understand what is a softener. Like we talked initially just before. If you allow fibers, molecules, yarns to easily be able to move in respect to each other, it's everything. The measurement itself starts from the bending rigidities. The measurement starts when you compress in your hand. And therefore, sometimes this property of softness is also referred to as the hand of the fabric. Stiff hand or a soft hand. That means you touch with a hand and you find it easy to bend. Why would it be easy or difficult to bend? We had answered earlier. They'll be easy to bend when any force that is applied, there is no resistance or less resistance. So if it is the fibers are free to move, if they are free to move during bending, then it will be easy to bend. If molecules also are free, that is the intermolecular bonding is less, they will be also easy to bend. So some materials are difficult to bend. By material itself, like this pen, you want to bend it, it's very difficult. On the other hand, this is paper. Appears very large, but still it is easy to bend. It's basically the molecular level, at a molecular level, the resistance offered to slippage is less in this case than in this case. And therefore, everything which has the softener or stiffener has to do with intermolecular friction, interfiber friction, inter-yarn friction, and this is will be experienced when you bend. If you don't bend, there is nothing. If you don't bend, there is nothing. The softness will be felt only when you bend, when you crumple. Only then you will talk about it. So, as a principle, when you want to make things stiffer, you will like to increase the intermolecular, interfiber, inter-yarn friction. Increase. For example, you take a cotton fabric, put it into starch solution, dry it, it becomes stiffer. Or you can use melamine formaldehyde based systems which can cross-link not just two ends or two functional groups, there can be 3 functional groups, there can be 6 functional groups, and if all of them somehow react, it will become a network kind of a structure, very, very solid, difficult to bend. Okay. So what does softener do? A softener, therefore, is like a lubricating agent. So if it is at the molecular level, so it's acting like a plasticizer. You may have heard of a name called a plasticizer. So if you add a plasticizer to any polymer, you will find it becomes softer, it is easy to bend, it becomes pliable. A lot of things keep on happening. But if in the case of fiber, you apply an oil, suddenly you'll find, well, things happen. And the oil is a good lubricant. In the day-to-day life, you're using these oils and fats and waxes as lubricants. So if you use them, they would have less friction. If they have less friction, then you would have the hand which will be softer compared to the previous situation. So how do we see the performance or judge the performance? The performance of a softener would be judged by what is the percentage change. Let us say you are measuring bending length. So what will happen? It becomes softer, the bending length would be reduced or will increase? It will reduce. So by what percentage the softening has happened can be somehow evaluated indirectly by talking about the change in the bending length of a material. Then you will say how much you have to apply to get the same change. So those material which would be required less in quantity and would give similar performance will be in a way will consider the better performers. So in general, silicon based softeners are used quite a lot because they actually can be very effective at low concentrations. On the other hand, they are polymeric also, and so their fastness to wash can be also improved. As far as the ionic softeners are concerned, what are we looking at? We are looking at what is the length of the hydrophobe, what is the nature of the hydrophile. If hydrophile is cationic, well, the advantage that you will get is that you will be able to, if there's a cationic nature of the softener, then you will get more affinity. That's what it is. Otherwise, the length of the hydrophobe actually will decide the effectiveness. So that is what one will have to worry about. So all of them will work in one condition or the other. Compatibility issues will have to be checked, but some of them you may not be able to use because of the components which are there part of the recipe, which may react with themselves. Therefore, non-ionics becomes important. They would not require polymeric softeners like polyethylene emulsion can be important. They don't react with anything, and because they are polymeric and not ionic at all, so they are not water soluble, they are not going to be coming out. So all of them will have some advantage, disadvantages. Cost may be one of the factors also. So in general, silicon can be more considered as more efficient, from that point of view. Some people wanted to know what kind of a bond silicon softeners or compounds will make. So there are two things in this whole thing. One is the alkyl group in this thing. So the alkyl group has a function to perform. Silicon oxygen base system makes a polymeric chain, so the length of the molecule can be increased, and so your wash fastness will reduce. So if you are only increasing the length of the chain with some methyl group there as a alkyl group moiety, then you will get a softening effect, But the same softener, when is reacted in a way, polymerized in presence of a certain type of catalyst, some of them could be zinc octoate and tin-based compound. These type of organometallic catalysts have a tendency to orient the silicon oxygen moiety within the polymer system. Silicon oxygen group is a highly polar compound, Howler group, and most of the uh, textile substrates also have some polarity. It's not a zero polarity. They have some polarity. And because of that, if this orientation can take place, then silicon oxygen bond, which is a polar bond, can make polar-polar linkages with the substrate and will help in orientation of the methyl groups towards outside surface other. Therefore, the actual surface which the environment, the liquids will come in contact with will be different surfaces. Like for example, many methyl groups getting projected out, and that is what going to be the projected surface. And now then, if that happens, that becomes a water repellent. But the bonding which is made invariably is polar-polar bonds. But there can be reactive things also. You have amino-based systems which can have affinity of a different kind also. You can have hydrogen methyl type of disiloxane, which the hydrogen part can actually react with anything which is available. Then you can make reactive systems also. So the bonds will be different, but in general, the silicon oxygen group, which is a polar group, will be able to make polar bonds with the substrate. Then there was a question on wetting spreading. So wetting, if you remember now, has been defined as the ability of a liquid to wet a surface. Now some of the liquid and these solid surfaces will interact more and some will interact less. Now this wetting depends on this interaction. Now you remember the Young and Dupre's equation. Okay, the surface energy of a solid is related to the surface tension of the liquid, and also is related to the interaction, which we had referred there as gamma SL. Right, rest is vapor. So surface tension of a solid or surface energy is solid versus vapor, liquid is liquid versus vapor interface. So these are the interface energies which are there. From the definition point of view, when I put a drop of water on any surface, it is going to take up a shape based on the equilibrium, and the equilibrium forces are going to be decided by these. Which are the things? The energy, the surface tension of liquid with respect to vapor, the surface tension of the solid surface with respect to the vapor, and that would mean some kind of interaction. Now if this thing changes, then the contact angle changes. So if the contact angle is less than 90 degrees, we call it positive wetting. That is, it is wet. If contact angle is 10, it is more wetted. Is 30, little less wet, but it is wet positively. If it is 70, it is still wet. Only at 90 degrees you would like to say that it is zero wetting. Zero wetting does not mean no wetting. Alright? And then you go, the angle becomes more than 90 degrees, then becomes an obtuse angle. So you say, now we're getting the negative wetting. Repulsion is starting more. You go to 140, the drop would just start rolling off the surface, we just incline. And so that is how the wetting part is concerned. So positive wetting, zero wetting, and negative wetting. But in some cases, like you have a fully scoured, bleached cotton fabric, you put a drop of water, you don't see the drop at all, it just gets submerged. It is spreading. If hydrophilic to hydrophilic goes, hydrophilic, very hydrophilic surface and water droplet, it is going to spread through the capillaries, through everything, and you see the area on which the drop was there continuously keeps increasing. This is not an equilibrium situation. Young and Dupre's equation has not been defined for such situation which is non-equilibrium situation. But this is spreading, means the liquid is going to spread in all directions based on the convenience, the amount that is available, and therefore we cannot even have a contact angle. We can't say the contact angle is 0 because this is not defined. At this, it just spreads. Okay, so difference between wetting and spreading, you can hope would appreciate this. Is that right or no? So spreading is a non-equilibrium condition. Contact angle cannot be measured. Is that right? So there was some question which probably was asked in one of the assignments, and somebody wanted to know. The question probably said whether the water repellent fabrics have to be necessarily breathable. And so some people took it differently and maybe did not answer it correctly. Let us say you have a cotton fabric. Okay, cotton fabric has a face and there's a back, and I want to make waterproof fabric. So what I do? Let's say I coat it from the back side of the fabric. Coat it with what? I can coat with anything. Let's say I coat it with a natural rubber for that matter. Okay, or a polyurethane film. I coat it on top of that, on the back side of it. So based on the strength, the thickness of the back coating, we will see the penetration resistance of this fabric would increase tremendously. Would you call it waterproof or not? So the proofness is not a one word or a one value. It is levels. Some can resist to up this much pressure, the others can resist to more pressure, some others can resist to still more pressure. So they become waterproof. Alright? So I have coated rubber. So most probably it is not going to be, the water will not be able to penetrate through. It's a tough one. But then I also decide that I will give a water repellent finish on the face side of the fabric. Can you stop? Can anybody stop that? I give it. So this surface becomes repellent. So just because the surface is repellent does not mean that it cannot be waterproof. So there are two independent things. Requirements are different. I like it. Inside I don't want. Only thing is the special case, which were the waterproof breathables. They are special cases. So while waterproof breathables are waterproof but still allow the vapor to go, they may not be water repellent unless and until on the top of the surface, the face of the surface, you actually give a water or oil repellent treatment. If you give them, they become repellent. If you don't give this treatment, they will not become repellent. So theoretically, a water repellent fabric can be waterproof as well. Right? So I think that should answer. So no confusion as such. But by definition, if you say water repellency does not require it to be waterproof. That's the only thing. But a waterproof material can be made water repellent. There's nothing to talk about. No confusion, I hope. Somebody also asked that if water repellent fabrics are there, whether these fabrics will repel a blood. Okay, this is the question. So we talked about the water-based soils. Did we talk about that? So what did we say in the water-based soils? If the water-based soils, aqueous-based soils are there, the water repellents can work. You see, a blood, for example, has about 55% a material called plasma, which is almost 95% by volume is water. All right. Of course, then you have the other material, red blood cells, which are about 45% or 44%, and then the white blood cells, and some other kind of materials also will also be there. So, a majority of it, if it is water-based, so we hope that you will get repellency. Now the question is, if you have normal silicon based water repellents, yes, they will repel. If you have fluorine based system, they will repel better. Alright, so that's how we like to put it. But yes, water based thing with blood is water based system. But you must remember this the blood and other things have some coagulation systems also. Alright. If immediately it is falling, then it can repel. But if it is allowed to dry, that it coagulate, then obviously it will be a different story, of course. You can still wash it off. No issues in that. Right? I hope this makes some sense. I think this question was on the forum and answered some time back. I thought I'll just take it up just to ensure that we are updated on this. Question probably said that if the repellent added are more, the fiber becomes better. I'm not sure what the question actually, what the student wanted to ask exactly is not clear. So fiber becoming better or worse is not a question. See, remember, in some cases we are interested in more wetting, right? You do all processing, chemical processing that you do, you want more and more wetting, aqueous. Alright? If suppose I want to do coating of a polymer on a surface, I would like the polymer solution must spread evenly, very nicely. If that happens, in that case, you would require more wetting to take place. So there's nothing better or worse. But if you require waterproofness, you give waterproofness. You want to give repellency, you impart repellency. So if you want repellency to oil, you go for fluorochemicals and go for the repellency of oil. You see, that will be interesting, is it? So all finishing treatments are supposed to basically improve one or the other functional properties. If they are contradictory, well, they are contradictory. So sometimes we compromise. Everything cannot be achieved, right? So we say, well, today we are only interested in waterproof. Something we will lose, yes, but waterproof for me is more important. So it's more important. There was one question as to what is a Zisman plot. All right? Zisman was one of those scientists who worked on finding out the surface energy of a solid. Surface tension of a liquid is easy to measure. You just put a drop, try to measure contact angle, do various kinds of things, dynamic and static, and try to get an idea. Understanding surface energy of a solid was also difficult, although Young and Dupre had given some equation which would actually say, well, this is the kind of contact angle. So say what is the level beyond which this surface is 100% going to be wet, just cannot repel. It will be just like a spreading, for example, could happen. Now what will be the kind thing? So Zisman and co-workers did many experiments, and then they found that if suppose you take many solvents for any surface, let's say tomorrow you're talking about polyethylene, so I want to see. So I will say how does the contact angle change with different solvents, different liquids. So you take standard liquids which have got standard, for example, surface tensions, and then put the drop of that particular liquid in a standard manner and see how the contact angle changes. If the contact angle is very high, obviously it repels. Okay, so for that particular solvent, this is going to be a surface which will repel. You keep reducing the surface tension, you will suddenly find, well, at a particular surface tension, it does not repel at all, it actually starts spreading actually. So you want to know that is the limit. How do you find that limit? So what it did, or these people did, was that they put various solvents, kept on measuring the contact angle and gave a plot of cos theta. Theta means the contact angle versus the surface tension of different liquids. And they found at a particular level of a surface tension of a liquid, the cos theta becomes 1. Alright? So theta is just 0, that means it's going to, beyond this if you go, that is below this level of surface tension of liquid, is going to spread. So I say, well, this is the limit. After this, if you are above this, this will repel. If the surface tension is below this, obviously there is no question of any repellency. You got some kind of a critical surface energy of this solid. That Zisman plot is the one which actually gave you this idea. Any other question which has come? Additional? No question? Alright, so we talk about some more things. One thing people had asked, is C17 more hazardous to environment than the C6? Now the C6, C17 has to be also qualified first. Okay. Are we talking about C17 hydrocarbons? Yes. So normally we have been talking about when the numbers have been high, we mean that it is a hydrocarbon, right? If you have methane to ethane to propane and keep on increasing the hydrocarbon chain length, the hydrophobicity keeps on increasing, and so we get some function. We're very happy with those functions. The question was, when you discard the material, what happens? So anything which was available as it is, like the hydrocarbon in nature had already worked on them, how to destroy them. Alright, like triglycerides and all kinds of things would be there. The soaps that we were making earlier, they were made from natural oils. So oils and fats are natural product, isn't it? If they are natural product, then nature had wherewithals to break these molecules into smaller molecules and finish them off, right? Despite being the hydrophobic. Yes, nature did not know how to make polyethylene. You have 100,000 molecular weight or more. If that kind of a thing happened, nature obviously became more and more difficult. But smaller molecules, C17, C25, they are quite, from nature's point of view, small molecules. The problem came when you talk about fluoropolymers. So that C6, what you're referring is a fluoro C6. C is there, but there's no hydrogen there. It's a fluorocarbon. Now this particular thing did not exist in nature. Therefore, nature had not been able to find solutions to break this down. So what happens? This particular part, also if you remember, we have a backbone of acrylic or polyurethane molecule over which these branches of fluorochemical moieties have been attached. Now, the fluorochemical moiety during hydrolysis, when you throw them off, can break down from the acrylic part of it or a polyurethane part of it, and it's separate and going into the environment. If this number is C8 and above, fluorochemical moiety, C8 and above, nature has hardly any way to destroy easily. So what you say, well, let it be available, no problem, if it is soluble. Then suddenly people found that C8 on fluorochemical are difficult to dissolve, C6 is more easy to dissolve, but C4 is highly soluble. So at least even if it is not destroyed, it still is water soluble. So somebody ingests it, it will go out of the system rather than get stuck in the body cells. You get the point? So from hazardous point of view, C17, C6 is what we are looking at. One interesting question somebody is asking, how can polyacrylonitrile fiber is a substitute for wool? So I don't think that is the way the question probably wanted to be framed. Polyacrylonitrile and wool are two different things. Okay, it is a synthetic material. It has some advantages. Wool is a natural material. It has some advantages. The most important advantage is it's biodegradable. So when you discard the material, it will just be sort of consumed by the nature, the enzymes and everything else. You have a lot of enzymes there. Now, polyacrylonitrile on the other hand, synthetic material, but it had some interesting properties which when people synthesized they did not know about it, but found out later that this type of material can actually be oriented without crystallization or substantial crystallization. So if you orient something and it doesn't crystallize, it is easy for it to shrink under a right kind of conditions. So they could make high bulk yarns using shrinkable, non-shrinkable acrylics. They would make fluffy yarns like the knitted and like the knitting yarns for the wool, exactly similar looking. And advantage, I mean, you take the reverse of it. Once you dye, the dyes are relatively more wash fast. The fiber is not biodegradable, so in general nothing will happen. You do not have to do dry cleaning of this. You can wash at home, while woolens have to be dry cleaned because of various reasons. And therefore, because they are easy to handle, brilliant dyes, and the warmth, by now you know, does not come from the thermal conductivity of fiber. It is basically the air which has been entrapped inside this. That is what gives you thermal conductivity. And so they were as good, much cheaper. And that's what it is. So they're not replacements. So those who are connoisseurs, they will still like to go for merino wool jacket. All right. I think that's all we have in this session. In case anything else is not there, so wishing you a pretty good rest of the course. Now what will be more important is that keep asking these questions on the forum as much as you want. I think we've been able to give you answers to various questions, and what is more important is that you try to understand the subject as it is rather than worry about what questions can be there, because neither there is a dearth of questions that can be asked, and nor there is anyone who will be able to answer all questions. The process of research is an important component. So first is the learning, that you understand the principles. So remember, we talked in this course is that this is fundamentally we want to know why something is done and what kind of approximate chemistry of molecules which should be there to achieve certain things. We are not really concentrating on recipes, what percentage should be added, what is the only temperature that you like to use. Different compounds will have their different optimum process conditions, including the concentrations, you know. So, but principles remain same. Optimization, in some sense, whenever let's say you become part of industry, you can do it. You get a new compound for that matter, which is also supposed to be a flame retardant. So it's a flame retardant. So what you do is you apply this new chemical to different levels in whichever way is the best method, and then try and optimize against what? Against maybe LOI, against maybe char length. Similarly for the water repellency, you may like to see how much is the repellency values in a spray test or a Bundesmann test. So you do the performance test and then try to optimize on these things. So this course basically is you to prepare you in some way to increase your inquisitiveness as to why something is being done, so that tomorrow you yourself can devise a new process, new method, new chemicals. Why not? So all the best. We keep meeting at the forum, and hopefully you will do as well as I expect you to do. All the best. Thank you.